Can everybody see my screen? All right, so I maximize the screen so I don't have access to the chat. So if somebody can speak up if there's anything on the chat, it would be good, okay? So in the previous class, we talked about a little bit about the CERN experiment. This is in the border between France and Switzerland, like is shown here. So this would be the border right there. And then the experiment is in both sides. There's a part that is on the Swiss side, there's a part that is on the French side. And if you go underground, as you can see in this picture, what you have is that there's several detectors and that protons are injected from here, they get boosted here, they travel around here, then they get inside here. And then there's actually two beams of protons being sent at each other until they collide, and they aim them so they collide at this position, which is one of the detectors. This would be this detector, the LHCb, or they put it in this CMS detector where the two protons collide. They have a huge detector here, or in this one, which is called ALICE. And again, this is underground 100 meters below. So you have two protons. They're not just two protons, there's a bunch of protons in there. In fact, there's a lot of current flowing by. So they keep all of those together. But the idea is that if you collide one with the other, they're collided at such a high energy at this position that when they collide, they're actually breaking apart into the individual components of the proton, which in this case is quarks and gluons. So quarks are the fundamental particles inside of protons and neutrons, another matter. So there's fundamental particles are electrons because they're point particles, they don't have any internal structure. And protons are not fundamental particles, neutrons are not fundamental particles because using this type of experiments, they have found that they actually have an internal structure. And the internal structure seems to be 3 point particles inside of them that are called quarks. So the difference between the protons is, and the electrons is that internal structure. So now it turns out that the quarks, we believe, are the fundamental particles because there's no experiment that has proved anything deeper than the quark. So these are very small, tiny particles, point particles, just like electrons. And the other thing is that the quarks are stick together inside of a proton with another particle that is called a gluon. So give me 1 second. Somebody needs to be admitted. All right, there we go. So the gluons are the particles that are more like springs that are getting those quarks together so that they stay together. So it turns out that if you have two quarks and you grab one of them and try pulling them out of each other, this gluon makes it so that it gets really hard and hard to push them apart. So you don't even see them individually. So quarks are inside of the protons along with the gluons. And that's what we see from experiments. Any questions so far? All right, so then let me get into the exercise for today. So today's exercise is as follows. Let's say that we had two protons coming at each other. So there's going to be a proton right here. And this is proton 1. This one is moving in that direction. So it has a velocity in this direction. And then there's actually another proton. Proton 2 is located here. They're exactly identical, except that this one has a velocity in the opposite direction. So they're headed for a collision with each other. Now, proton 1 and proton 2 are initially moving at the same speed in the Earth reference frame. So this is the Earth reference frame. That means if you're looking at them, this is the first before collision, the first time that you see them. And they collide head on. And then when they collide head on, there's actually, after collision right here, we actually see that there's a new proton, proton 3, a neutron right here, and then another particle that is called a pion. Again, this is in the Earth reference frame. And these are not moving, so they're at rest. All right, so we have proton 1, proton 2 initially moving at the same speed, opposite directions, they collide head on. After the collision, we see that the products are a proton, a neutron, and a pion. So in terms of masses, the mass of the proton is going to be our unit of mass at this point. So the mass of the proton is our unit of mass, and then the mass of the neutron is actually not exactly, but very close to the mass of the proton. This is 1.0014, the mass of the proton. And then we also have the pion. And the pion is a new particle. You probably haven't heard of it before. This pion has a mass that is 0.1488. Mass of the proton. All right, so this is in one reference frame. So now let's say that we were in another reference frame. So now let's say that we were looking at the same events, but now this is from another point of view, okay? So in this point of view, what we have is that there's a proton 1 right here, and it's moving and supposed to be straight direction just like before, with a velocity in that direction. And then we have a proton here, and this proton 2 is going to be at rest. So now your frame of reference is the reference of proton 2. And then after the collision, what you would see is that you will have that proton 1 is located here. No, sorry, now there's a proton 3, a neutron. They're about the same size like I told you before. And then the pion right here. And they're all moving together in that direction. So let me put all of them are moving together in that direction after the collision. This is in the proton 2 reference frame. All right. Any questions so far? All right, so here's the question then. The question is, in the T2 reference frame, comma, what is the ratio of kinetic energy of proton 1 to the internal energy of proton 1? So that's the question that we're after. So now, what have I given you? I have given you the description of the system. There's two protons colliding. They create another proton, a new proton, a neutron, and a pion. You know that the initial mass is of the in the two reference frames, and you know what the final masses of the products is at the end too. So now the question is, how do you calculate this ratio, right? In this second reference frame where everything is at rest. So we have these sketches. Do we know what velocity is in the first one? So what do we want to do? Figure out how fast these two guys are moving, right? So that the total mass in reference 1 so the total mass in this reference frame of the Earth at 1 is how much? Anybody? What is the mass in this reference frame?
Wouldn't it be 2 MP?
Exactly 2, right? And then in the second reference frame, we know now that the mass is not 2, but it's actually 2.149, well, 2.15, right? Close to 2.15, because these two guys are there. So what happened is that all of this kinetic energy got converted into mass. Does that make sense? So that's the first thing that we need to figure out. What is that speed that they're both traveling at the beginning? So that's the first task. Should I send you guys into rooms to figure this out? And let's see. Breakout rooms, and then we're gonna have 2 rooms, and you're assigned to them. All right, so you guys can see my slide now, right?
Yes.
All right, good. So now, what was the speed that you guys came up with? Or do we have a speeds from each of the rooms?
So wouldn't the speed in the second reference frame of the first proton be twice the speed of the protons in the first reference frame?
So that would be classically, right? If you were doing this classically, that would be correct. But let's say that in the first reference frame, just as an example, let's say that do you guys see my mouse?
Yes.
All right, so let's say that this guy was traveling at 2/3 the speed of light. This guy is traveling at 2/3 the speed of light. Classical mechanics would tell you that then in this reference frame where this one is addressed, this one would be traveling at 4/3 the speed of light, which is impossible, right? So that's where we would have to look at this particular equation over here, which is the relativistic way of doing things. So this brings me back to something that I wanted to remind you from the previous class. Is the internal energy invariant? Yes. And then is the internal energy conserved? No. But the total energy of the system is always conserved, right? But it's not invariant. So those are the key to solving this issue right here that we have. So I have 2 reference frames. Let me call this one I'm giving you the right names for it. It's not as what I had told you before. But then we have that this is the 0 momentum frame, because if you look at this one, the momentum is going in this direction for proton 1, and the momentum is going in this direction for proton 2. Now, if you look at the momentum here, the momentums cancel out because they're exactly the same mass, but they have a different direction, therefore they cancel out. So this is called the 0 momentum frame. And then afterwards, you see that there's 0 momentum because even though they're massive, none of them is moving. All right, so then the other point that we have is that here, there's momentum from this guy, and there's nothing to cancel out going in that direction, so the total momentum is here, is the same total momentum over here. Does that make sense? The momentum would be this mass plus this mass plus this mass moving at a particular speed. And in this case, we have momentum conservation just as in this case. So we're able to figure out how fast this is based on how fast this is moving. But then the other thing that we have is the momentum is conserved in this reference frame over here and here. And we're able to tell how much energy was before in the system because it's the internal energy of this guy, right? Which is related to mc squared. The internal energy of this guy, also mc squared. And then the total energy also involves the kinetic energy, which has this mc squared of each of the particles and whatever speed they're moving. And those two added together have to give you back the same total energy over here. So if we look at this first one in green, for the zero momentum case, right? What is the total energy of the system after or before? We should be able to know what is the total, right? After the collision. Because we know that the three collided together. And we also know that the kinetic energy after the collision should be zero. Do we agree on that? And
Yes.
we know that the total energy so it would be the kinetic energy of proton 1, proton 2, total energy so total energy is equal to kinetic energy of proton 1 plus kinetic energy of proton 2 plus the internal energy before, which is equal to the internal energy after. Those two are equal. So we know what this guy is, right? And let me put the numbers back in, which is mass of the proton. Oh, that's not good. We would have mass of the proton plus the mass of the neutron, which we said, well, let me do it this way. Mass of the proton is my unit of mass. So I have that the mass of the proton is 1. The mass of the neutron is 1.0014 plus the mass of the pion, which is 0.1488. So that's all of the masses that I have. And now I need to put in c squared here. Can you guys see the c squared? I don't know if it's part of the board right there.
Yeah, we can see it.
All right, so now you can figure out how much the kinetic energy is, right? Because you're gonna equal this to this, but this one is mc squared. This one is mc squared. No, wait, my bad. My bad. This is unknown. This is unknown. But this one is 2mc squared. All right, so do you guys want to figure it out on your own and then shout an answer, or you want to go into the breakout rooms and work together? Breakout rooms or not?
We're solving for KP1 and KP2, right?
Well, they're identical, right? But yeah.
Okay.
Exactly. So staying here. So whoever gets it, let's see what you got. All right, anybody has it?
So should Kp equal 1.0751 times mass of the proton times c squared?
Sorry, say it again.
1.0751 times the mass of the proton times c squared.
So what I have is I added these two guys together, right? So I have 2 Kp because they're identical. And what I have to get is 1 plus 1.14 plus pum 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 minus 2. So this minus 2 divided by 2. Does that make sense? So it's,
yeah, I think I just added wrong.
Okay. So once you get that number, you can actually get the next one, which is lambda, right? Just using this and canceling out the MCs. And I get that this Lorentz factor for me is 1.0751. So now you have used that Lorentz factor before. You have used it before to figure out what the speed was. So you don't need to do it at this point, but this, I could write out the equation for it. The Lorentz factor is the one that has You used it in contractions, you used it to find velocities before. So let me write it right here. This gamma Lorentz factor is defined as 1 over the square root of 1 minus velocity squared over the speed of light squared. So what that means is that I can write out the velocity at this point of the protons, right? The speed of the protons. And I got 0.367 speed of light. Any questions about that? I just want to speed it up so that we don't have, so that we have enough time to get to the punchline. Any questions? All right. So once you have that speed, what would be, how would you go about getting, so we have all of this. We now know what is this speed that this one has, the velocity is going in that direction. We know the speed that this one has with this velocity going in that direction. So we have this one. Now, we don't know how fast this one is because you don't add the two velocities together, right? So the velocity of this guy, when this one is at rest, so basically if you were writing this proton and you were going at a speed of 0.367, the speed of light, but you're on top of it, you wouldn't feel like you were riding that thing. You would feel like you're at rest on top of it. You're not accelerating, you would be going at that speed. And then you would see this one coming, but you wouldn't see it coming at 0.367 times 2, right? You would see it at another speed. But now we have that all of this momentum that is generated here, which is, and I think I haven't given you this, but this is the conversion. So momentum used to be just MB. Momentum is actually Lorentz factor times MB. So that's something that I hadn't given you before. All right, so here's the next thing I want you to do. So this is a vector. Let's not forget that because this portion right here of the velocity is a vector. So here's what I want you to do for your homework. We know how massive this is. Here are the masses, right? And we know that energy, right? Let's go back over here. Internal energy is invariant, and then its energy, total energy, is not invariant. So that means that the total energy that I found over here is not going to be the total energy that I have down here in this other frame of reference. So when you have this, what is it then that you have to do? You cannot use the total energy above and say that it's the same as the total energy below. But can you use momentum? That's a question for all of you right now. Is momentum going to be conserved down here? Is the momentum going to be conserved in this collision between this one and this one? What do you guys think?
No.
Sorry?
I said no.
Actually, yeah, momentum should conserve. So momentum is always conserved, right? Just like energy is always conserved. So momentum is conserved, and you're able to go from whatever momentum was over here to whatever momentum these three guys have, and the speed is not gonna be the same value, right? But this should be conserved. But remember that this speed is gonna show up here, not just here. So it makes it a little bit complicated. So the question is, what is going back to the question, what is the ratio between the kinetic energy of proton in this reference frame? What is the ratio between the kinetic energy of this proton and its internal energy? So the ratio between kinetic energy of this proton in this reference frame and its kinetic energy. So we have several internal energies already, because internal energy is related to the mass. And the one thing that we don't have yet is how much it's on kinetic energy over here. This one has 0 kinetic energy. This one has all of the kinetic energy going for it. And last, I don't know, you guys have questions about how to solve it? Anything that is not clear? We have a couple of minutes before class has to finish. That's your homework assignment for this next class.
So we're solving for the kinetic energy of P1.
In the second target reference frame, right?
What is that the gamma thing? Is that the same for all of them?
No, gamma is related to the speed that you're moving with. So gamma is, here's the speed squared over the speed of light squared.
So the Lorentz factor is different for the two different reference frames.
Exactly. So let's see, I have a minute. Let me give you a hint over here. So we have that the initial kinetic energy. Where's my mouse? There we go. All right. So in the target reference, in the target reference frame, we have that the kinetic energy final is going to be given to you by so we have actually that this one is traveling with a particular velocity and this one is traveling with a particular velocity, right? These three together. So we're going to have that one going at a velocity v minus 1 of the proton c squared plus the neutron c squared plus the pion c squared, mass of the pion c squared. Okay. And this one right here is 0.0751. So now that you have the final kinetic energy and the internal energy final, then you can now go look and figure out what is this total energy on this end compared to total energy on this end, and figure out how fast this guy is going. Or in this case, just get the ratio between the two, internal kinetic energy and the kinetic energy before the collision, once you have those values right here. So you have to relate kinetic energy, internal energy over here, kinetic energy, and internal energy over here, and you're good to go, okay? So I need to finish class at this point, but if you have questions, I'm available still.